And great to be here, thanks. Good to see everybody. So this is going to be focusing on my experience with analog electronics. So just a little bit of context. I started on the open source ASICs in 2020 when Tim Ansor announced the free tape-out opportunity. So without that, I definitely wouldn't be here, wouldn't have done any tape-outs. So that for me made a huge impact, and that was all live streamed on the FOSSi dial-up during the pandemic. And my first tape-out was in December 2020. And this was my first ever chip, which took over a year to come back. It's a long iteration time, not like VGA Playground. And how do I press this? So I started off with my analog journey, doing something really, in hindsight, ridiculous, which was like a hand layout of an inverter. And I didn't really realize what I was doing at all. I knew what an inverter should be with the PMOS at the top and the NMOS and how they were connected together, and I drew it all out in Magic. And it took me probably like a couple of days to get a DRC clean layout for the first time, and then another 2 or 3 days to simulate it for the first time. And then when I did that speed run, it still took me like 12 minutes after a lot of practice to be able to draw an inverter that was going to work. But there was a lot of stuff there that, like these bars at the top, I didn't even know what they were at the time. I just copied them because I was copying from a standard cell, and those are the bars that join standard cells together. So if you were actually doing an inverter, you're drawing it out, you probably wouldn't put them there, but I was just totally cargo culting it. Okay, now next, how do I go next slide now? Next slide, there we go. So a bit more context. So yeah, I got the first chip back in early 2022. And in this time we were doing the Google MPWs, and we did the first beta of Tiny Tapeout 1 in September of 2022. And up till that time I was mostly focused on digital, because I came from a bit of a digital background. I'd done some FPGA programming. And looking back on it, I think I just took it completely for granted, the incredible power you get with digital abstraction. Like, you assume everything is ones and zeros in the computer, and all the numbers add and everything multiplies, and you get the pixels on the screen and everything's great. And in one line of Verilog, you can instantiate 1 million transistors. Small teams can very quickly create very complicated designs, but in the real world is analog, and those ones and zeros are real voltage levels. And the big difference between the 1 and the 0 means that it's very noise immune, which is great. So computers are usually very reliable, unless you get hit just in the wrong place with a cosmic ray. And then you realize, oh yeah, at the end of the day, everything is analog levels, numbers of electrons sitting in gates of capacitors and transistors. And even the digital blocks that we're used to using inside chips when we're doing our chip design, like memories, they're very analog at the end of the day. Like the sense amplifiers, the decode logic, a lot of it is very analog style. And my opinion is now with the tools that we have and the PDK that we have, the most interesting niche for open source ASICs is in the mixed signal zone. Because if you're just doing digital, you're almost certainly going to get a quicker, faster, cheaper result using an FPGA or a microcontroller. But with mixed signal on an ASIC, you can't get that any other way. And 130 nanometers is actually ideal for mixed signal. And many professional analog engineers are using these like more mature, older processors because they have great analog performance and they're cheap. So I kind of was realizing the importance of analog, and that I was going to need to learn it at some point. And I was that painful process of spending a week drawing 2 transistors and getting it to simulate. I was like, I want to be able to teach people analog without having to install Magic, do like DRC, set up ngSpice, do the extraction, do the simulation. So I collaborated with Uri Shaked, and we made SiliWiz, Silicon Wizard, or SiliWiz, as I like to call it. This is probably going to be a bit difficult for me to do over here, but and it's massive as well. But you can delete and redraw a gate of a MOSFET just in like a couple of clicks. And I don't know if I can. Oh, there we go. I've messed up this inverter because I haven't. Let me just see if I can hack that on there. Yeah, look at that. So I managed to get the inverters back working. So this is again like more great Uri Shaked stuff. So Uri did the VGA playground. This is, we've got Magic at the back end sending for DRC and circuit extraction. And then we compiled ngSpice for WebAssembly to run it in the browser so we get this instantaneous user feedback. So I won't try to do it now because this would be terrible ergonomics, but I can do a CMOS inverter in about 2 minutes now instead of 5 days. So this is a really great educational tool, and it's just on the browser. So if you want to teach this, then you can check out the lessons that we've got here. We've got like a set of lesson plans there. So that's SiliWiz. Yeah, the lessons cover CMOS and the PDK stack up, parasitics, resistors, capacitors, and building up to an inverter. So moving on a little bit to 2023, I was in the mind state that I knew that analog was important. I wanted to be able to do it with Tiny Tapeout, which was only digital so far. So I started collaborating with Harold Prettel, who's also very involved in the open source ASIC scene, and he is the maintainer of the OSIC Docker tools, which is a very easy way to get started. You install this one Docker and it has everything ready to go. And most importantly, he's committed to maintain that. So every 3 months he kicks out a new release. And that's one of the dangers of starting open source projects, is you start them up when they're fun, then when you get tired you don't maintain them. So it's great that Harold is committed to keeping it going. He's using it for his teaching now. So he did a ring oscillator. This, apologize for the graphics, I should have updated them for a white background. But he did a simple pair of designs that we put on a Tiny Tapeout 5. That was one of only 2 analog designs, and the first one, they were just permanently connected in there. And he recommends that the open source tools are a great way of getting started as well, without the encumberment of NDAs. And this was my first actual analog tape out. So I'd done a bunch of simulations and I'd done some drawings, but this is the first time I taped something out. And I did it with no schematic or no LVS and no simulation. I just drew this in Magic. You only live once. Back to my roots. So there's just a little voltage divider at the top there, and then the biggest capacitor that I could fit in by putting this, like the biggest capacitors you can build at 30 microns by 30 microns. So I just stuck 60 of them in there. And then the idea was I could just measure them with a signal, with a scope and a signal generator when they come back. So I continued to learn, and I thought a great way of learning is by doing. So you probably already know I've got the 0 to ASIC digital course, so I started the 0 to ASIC analog course, and I was like, okay, this is how I got started. I sold tickets to a course that didn't exist, and then after I saw that there was a demand, I was like, okay, I'm going to have to sit down and actually build this thing. So I did the same with the 0 to ASIC course analog edition, and to make up for the fact that I really know a lot less about analog, especially back then, than I did digital, I made an agreement with Harold, so I pay him to come and sit in on the monthly calls, twice a month calls, to answer any questions that I can't answer. So we're all learning together, and he's like the backstop, 20 years of RF analog ASIC design experience, make sure that we can answer all the questions. So that was the first cohort. We've done 3 cohorts now of beta testing. I'll tell a little bit more about that later. But through development of that course, this is the kind of the top takeaways, like the top differences. How does analog design compare to digital? And unlike the cool demo scene stuff that we saw, is with analog, generally you have to be way more specific about what you're trying to achieve and set down a specification, because it's very, very manual, very iterative. So if you get all the way to the end and you realize your layout isn't meeting your spec, you might have to start the whole thing again, and it's very labor intensive. Simulation is longer, harder to get working. It's also not as portable, so a digital design, you can take that, put that into a place and route with a different PDK, and it'll probably work, and you'll get something out that when you tape it out will work. But with analog, things are very dependent on parasitic capacitance or like the thickness of layers. It's way more sensitive to actual layout, so it's way less portable to other PDKs. So more name dropping, Professor Boris Merman, chair of the IEEE Solid State Circuit Society. He's been teaching for a long time, did 20 years at Stanford and has now moved to the nicer life in Hawaii. Good job, Boris. And he's now switching over to teach with the open source tools and thinks that it's going to be really important for improvements in design methodology. He's written a bunch of books and they're all published on GitHub, so if you want to get into the heavy stuff, then check out his books. And this is kind of interesting because it is the parallels between doing board level PCB design and analog microelectronic layout design. And one of the things that I think is super interesting is for board level design, you can usually order off the shelf components at very specific tolerances. And with a wafer run, every wafer, although they are incredibly the same as each other, just very slight differences and deviations in thicknesses leads to different properties. And maybe people here are familiar with like slow and fast corners and these kinds of things. And you will have this variation of the design over the whole wafer. But components extremely close to each other will be extremely well matched. So the way that you do analog design is you do it all with ratios of things. So having said that, can anyone guess what this tiny tape-out design does?
Works out pi?
Yeah. Yeah, it's a voltage divider that outputs pi, because we're dividing the circumference by the area. And this is a design by Tomasz. Where's Tomasz? So if you want to talk more about how he did this design, you can talk to Tomasz later.
Lightning talk.
Lightning talk on pi tape-out. It probably also works as an antenna. Yes, ASIC hat, look at that, represent. Okay, so then this is kind of what I've settled down with my analog flow, and I'm mostly copying from what Harold does. So start with the spec, then you do the schematic capture with Xscheme, simulation with ngSpice, you can also use Zeiss. I do the layout with Magic, you can do K-layout, but you're going to have to use Magic anyway for parasitic extraction and DRC, stuff like this. That support is coming for K-layout, and I know that K-layout is the chosen tool by IHP, so the support is coming. DRC and layout versus schematic is with Magic and NetGen. So Magic can extract the circuit that you've drawn from the physical layout into a netlist, and then you can re-simulate that with Spice and check how close it matches to your original simulation. And there you'll be picking up all the unwanted parasitics and capacitances of your layout, so you might get a different result. LVS stands for layout versus schematic, so that's like if you misconnected a wire, then at that stage it should tell you the circuits don't match because there's a wire missing. And that is really crucial, it turns out. You definitely want LVS when you're doing this. It's so easy to make a mistake without it. Post-layout simulation, already mentioned that. And then once you're finished, then you tape out. But you see these like return loops. Like if your post-layout simulation doesn't match what your specification is, you might have to go right back up to the top and think, okay, I didn't account for that parasitic capacitance. I can't get these things any further apart or closer together. So I'm going to have to assume I'm always going to have this capacitance, add that into your netlist, and then adjust the rest of the circuit to take into account. So Tiny Tapeout 6 was the first time we publicly supported analog on Tiny Tapeout, and all the green tiles here were the analog designs. We've got enough spaces for 32 of them. The smallest is 2 tiles, and the biggest, at that point we didn't limit it, but the biggest is now 4 tiles, and you can have up to 6 pins. And we actually charge extra for the pins because the pins connect to a parallel bus via transmission gate, and the more transmission gates you have connected to those buses, the more parasitic they are, the worse performance there is. So we kind of incentivize you to not just use all the pins because you can, because then that makes the design less good for everybody. So yeah, so these are the designs here, and then these little strips here. If I just zoom in again, actually, there we go. So this long bar on the right-hand side is a big power gate. So this is part of the big infrastructure work we had to do this. When you're doing like digital designs with OpenLane or Coriolis or Silicon Compiler, usually the output that you get is going to work and it's not going to kill the chip. So up until this point, we just put all the designs on and we're just fingers crossed one design wasn't wrong and take out the whole chip. With analog, you just can't do that because it's too easy for somebody to submit a design that's like a direct short from bus to ground. So every design is now power gated, and that actually is better for everybody because it's better noise performance, better signal integrity. So in Tiny Tapeout, from 6 onwards, every design is powered off unless it's enabled, and then it's powered with this power gate. Again, thanks to Harold Prettel for helping out with the very many fingered mega transistor. That is all just one big long transistor here. And then at the top there, this design has 2 inputs, and we've got this transmission gate here. So then that is enabled. It connects those pins to the analog bus. And on the bottom left is a simulation of the frequency response we're expecting for that. And Sylvain Minot's done a lot of work on the integration work, and he did the layout for the transmission gate. So these were my kind of next designs that I did with schematics, you'll be pleased to hear, and LVS and post-layout simulation. So I did the whole thing. This one was my first mixed signal design. So I've got a digital block there and a R2R DAC here. So this one just generates sawtooth waveforms and drives the DAC. This was the 0 to ASIC analog course beta testers submissions. It all went on the same tape out. And then this came from, I think, it's Vincent Fusco, who did, this is a 555 timer, very pleased to start getting some cool old school analog on Tiny Tapeout, who's a professional IC design engineer, and he's super happy that for less than $1,000 he can do analog tapeouts now. This is an 8-bit SAR A to D, which should be pretty high performance because it was done by Dr. Carsten Wolf, who's a principal IC scientist at Nordic Semi. And I interviewed him about it and his experience here, which is well worth watching if you're interested in analog stuff. Again, he's a guy with loads of experience and very into what you can do with the open source tools. And one interesting data point I learned from him is that Nordic, who do a lot of the IoT chips, all of their old chips, like up to 3 or 4 years ago, were all done on 130 nanometers. So there's still loads of great value you can get out of these mature nodes. Okay, so yeah, this is one from Ray, a classic 8-bit programmable sound generator with a digital block on the top and then these 3 analog D2As. And one of the things I love about analog is it's often difficult to see, but you can see things from the layout. So you see this like exponential growing length of the transistors. And that's because it's trying to drive audio the way that your ears will hear it, which is in a logarithmic way. So you see like the logarithmic layout in the analog design. Tiny Tapeout 7. Again, like very good usage of the analog blocks there. Here's some more of mine. So I did a voltage reference, which was, looking back on it, too difficult for me really. Very confusing circuit that I still couldn't explain to you. Twin T oscillator was pretty cool, and I got a good handle on how that works. And I reused an op amp done by other people, so that was my first time reusing other people's IP. And I basically just I designed a notch filter, put it in the feedback loop of an op amp, and that makes an oscillator. So just like a 2 or 3 megahertz oscillator. And then this was from the beta version 2. So we ran that a second time, got a whole load of new layouts there. Other notable designs on Tiny Tapeout 7 was a 12-bit SAR by Ricardo Nunes, who did it for a master thesis but didn't have the opportunity to tape it out. And this is one of the things that Tiny Tapeout is for students at universities to actually do tape outs and not have to wait for PhD level. So he's now a professional at Texas Instruments, and he went back in time, converted his layout to something compatible with Tiny Tapeout and taped it out with us. Tiny Tapeout 8 was the one that we just did, and we enabled 3.3 volts analog supply for that. And it was my first time doing GDS art. Yes! 4 years later, I finally managed my first GDS art. So this is a ring oscillator, and then on the left, I upgraded my R2R DAC to make it a 3.3 volt with these drivers along here. And it's also my first dual rail design. And then this is the predicted output that we're expecting from that 600 megahertz ring oscillator. So in the pink is what we get in the chip, like that perfect rail-to-rail signal. And then you see it degrade as we go through the pads to the output of the I/O of the chip, because those I/Os aren't really rated at that frequency. We've done quite a lot of work on the model of the pad, and another tool that Uri's built is this X-Scheme viewer. So this is a way of you can easily share, you can just like put a link to a public X-Scheme schematic and then have it browsable and shareable on the internet. So this is the transmission gates here, modeling the capacitive load of the transmission gate, and then this part here is the model of the actual I/O pad. And we're expecting maybe a few hundred megahertz bandwidth on the analog pins, so that's maybe like 4 to 5 times better than the digital pins. So one way you could get better performance in the future, if you really need faster performance, is to use the analog pins to get better bandwidth. I'm going to have to go back to here. Beta cohort 3 of the course came up with some more cool designs, had some more professional people on there and some more complete beginners. And then this is a bit of info about how to submit designs for Tiny Tapeout Analog Edition. You just need the GDS, the LEF, and the info.yaml in the right place in a GitHub repository. And our actions will run all the DRCs and the checks and build you the 3D viewer and the 2D viewer. And this is the top level kind of limitations and max ratings that we have at the moment. So 6 analog pins, 3.3 volt maximum, a few hundred megahertz, about 10 milliamps is the maximum you can draw, and all of these specs are on that specs page here. Oh, and Tiny Tapeout 9 is open now, closes on the 10th of December, so get designing. Pricing, actually this pricing is a little bit wrong, I realized after doing it. One thing that you should know is tiles and PCBs are sold separately. Tiles and ASICs are sold separately. So for a university, you could have 10 students with 10 separate tiles, but just order one ASIC. So that makes the costs cheaper. If you want to do a 1-pin analog design and receive the PCB and the ASIC, it's $250. So that's how low we've got the price for doing analog microelectronics now, with real tape outs on ASICs, which I think is absolutely amazing. Results. We're in the unenviable situation of having like 3 Tiny Tapeout shuttles in flight. So we've only received Tiny Tapeout 5 back, which luckily didn't have any problems, because you only figure it out when you've already committed another 3 to the fab. So this was testing Harold's design, and we got the DAC and the ring oscillator both to work very nicely, so that's great. And if you want to see the video evidence, check that one there. We're expecting Tiny Tapeout 6 back in the next few weeks, and that's got like 30 different analog designs on it, so that'll be fun to test. Next steps, What is missing? So I really think that doing a radio would be great. I've been talking with Harold, and we think that a Bluetooth low energy is feasible. He's going to start doing some work on it with me soon. And we're missing like a couple of important things from NG-Spice, but that is, Holger was able to hire somebody, and he's now hired Kamil Pelka, who's now working on those missing features. And then for more advanced radio stuff, we're still missing some important stuff on the analog simulation side and the EM simulation side. So we're gonna build up to the Bluetooth low energy, but I'm going to start off with doing something extremely simple, like that 600 megahertz ring oscillator also got another one next to it, and I can enable them both. So I should be able to do frequency shift keying, just stick a piece of wire on the output of the pin. If I'm close enough with my spectrum analyzer, I should be able to pick it up, and that's a radio, right?
Yes, as long as the FCC's not.
Yeah, as long as they're not looking, I'll be fine. So yeah, I think the radio will be a great demo, and it's something I'm interested in. So I'm going to try to build up to a very simple, small radio application and start taping them out. And just to finish off with, I wanted to share some resources. So I'll share the link to this slide. If you're interested in getting deeper into it, then I've prepared some resources. So these are like all the tutorials and guides that I've been using and following. A very simple way of getting started with the tools is to use the Tiny Tapeout VM, which you can just download from GitHub and has everything you need installed. Also recommended is Harold's ASIC tools, Docker. My 0 to ASIC analog course is soon going to be available, and people have been enjoying it and doing tapeouts. It doesn't cover circuit design. That's crucial to mention. So that's like a whole extra course, I realized. So you need to come with a schematic that you want to tape out. I'm afraid I am not expert enough to teach you how to design analog circuits yet, just how to convert them into an ASIC layout. And if you're interested, you can sign up for the waitlist. And then these are my links and the links to the slides. I didn't ask at the beginning, who's academic here? Okay. If you're ever writing a paper about a tapeout that you do with Tiny Tapeout, you can cite my recent IEEE paper, or if you want to share it with your department, that's a good resource. Who's industry? Okay, interesting. More industry. And who's other? Shout out what other is?
Hobby.
Hobby? Hobby? Cool. Okay. And who's done tapeout? Okay, well, like maybe we've got about 80 people in the room, and that's like about a third, I would say. And who's done a tapeout on Tiny Tapeout?
Oh.
Not bad, it's about 10 people. Who's going to do a tapeout on Tiny Tapeout? Come on, all the hands up. Yeah. Okay, so thanks very much. That's it from me. Thanks for your time, and I'll look forward to having a beer with you later.
Awesome work, Matt. I have a question about, so for digital IP, you can stick that in a CI pipeline, right? You can test that, you can download it to an FPGA, you can look at the results, you can kind of try for yourself pretty easily. But as we build libraries of analog IP, how are we going to know the performance or the characteristics of this of these blocks?
I'm glad you asked that question.
Yeah. Well, in my head, I envisage like maybe a standardized reporting format, like silicon evaluation format that we can stick on the GitHub, check it in, and say, exactly.
Yeah, there's a recent tool made by Leo Moser and Tim Edwards called CASE, C-A-S-E, and they presented it at the Free Silicon Conference, so the video is up.
And Latchup.
And Latchup, yeah. And it's basically something that can run a whole sequence of tests, get the outputs, and then can put them all together in a data sheet, and then that can be part of your CI flow.
Amazing. And that's against the silicon?
No, that's against the
simulation.
The simulation. But that's also a very important thing, is that out of the maybe 400 or 500 designs that were taped out on the Google MPWs, only like 5 or 10% of them were ever tested which is really a shame. I can understand why, because it takes so long to come back and you often need special equipment and you didn't document it in the first place and now you've forgotten how it works and you're busy and you've moved on to other things.
Yeah.
And we have like a system that when you plug the demo board in, you use a web app to choose which design is active, and then there's a button there that says test and report this design. So we've made it incredibly easy to report results back, and we still only have like a couple of hundred reports back out of the 1,000 designs so far taped out. There's 3 chips in flight that people don't have yet, so that does skew the numbers. But this is also, I think, a very powerful thing about Tiny Tapeout is that if I make something cool but then I lose interest, you with the same chip have access to my design and you could test it. And that's also great if I live in a country where $50 or $100 is a lot of money, and I can't afford the chip. I could still tape out an analog design. Then I could talk to you with test equipment. You could make my measurements and send them to me, and then I could publish something with my layout, my schematic, and my silicon results for just that $50 or $100. So we also want to democratize the testing and characterization, and that's something that I'm working on actively at the moment.
Fantastic. I'm pleased to hear that, because that is, as you say, so important to the evaluation of the block. If we're going to see reuse of these things, people need to be able to know how it performed. And it's a really good point that people can just buy it, and I don't know, imagine they want to see how it performs in a different environment before they modify it. They can get their hands on on the design in silicon first.
Totally.
It's a great point.
Yeah, I want to comment there that designing a chip that you can test, that you can measure the same metrics that you can simulate, is an art in itself. So if you can simulate something, likely you cannot measure the same thing on a chip. So you really have to design for that, and that's an art in itself, and a whole more difficult, I would say, than the analog block itself.
It's actually one of the objections that we have with Tiny Tapeout is it takes so long. What do you do with your students while you're waiting for the tapeout? And one suggestion is the students bring up last year's design, and as they bang their heads against the lack of documentation and how hard it is to test, they are learning how to design for the next people to test. And that's a very important skill that is hard to learn. And to be honest, it took me four or five tape outs to learn it myself, because I taped these things out, and if they didn't work, I didn't have access to those internal signals anymore. So now I have like a couple of pins on my design, and when I enable debug mode, now I have access to other parts of the design.
I think in industry, there's a few areas where I guess I would say modern engineering practice hasn't really reached analog design. I mean, one of them I think is revision control. You have things like IC manage, right, which sort of do revision control, but in a really weak way. And I wonder if the open source community could contribute best practice there in terms of analog design. I mean, it's one thing just putting your circuit into GitHub, and there's a certain amount of reusability there. Although I think IC Manage does like a little bit more than that, in that it introduces these concept of component libraries and that sort of thing. But I wonder if there's any tools in that space that you're aware of. And another thing that industry's done really bad is any sort of automation of analog layout. And you have things like Agile Analog, the startup, which is trying to do some sort of automation of analog layout. But obviously it's really hard because, as you say, it's very iterative, and that's a hard thing to build a tool around. But it's also something where it seems like the open source space could do some research there, do some experimentation. Are you aware of any projects in that space?
Well, like when I look at my designs that I've taped out, I can go back through every iteration and see the layout and the simulation results for each one, because that's all part of the GitHub Action history. And if I used Case as part of my CI, then I would also have that data sheet generated for each version. So that's maybe halfway there.
Yeah, I think that's something where, because the industry is so segmented and you have analog designers who have come through a particular style of working their whole career, and they're really not exposed to what's happening in the rest of the EDA industry.
Yeah, like this quote on the left.
Yeah, that it's really an obvious win, where you just take the things that work well in other parts of the semiconductor industry and apply them to analog design. You know, you have the big issue that the designs aren't portable, which makes it a lot harder to do things like have a useful GitHub. But it's something where I think the open source community could really innovate.
Yeah, yeah. And I think, like, also going back to your question, like closing the loop on the measurement and the characterization is also crucial and just really still very missing, still very, very patchy. Yeah.
But yeah, certainly one step at a time, right? And I mean, it's super encouraging.
Do a BLE radio.
Yeah, well, I think that's an awesome idea. I think that once you've got the different components, you know, like a band gap and PLL and all these things that have been designed and validated on silicon, I don't see why you couldn't put them all together and start playing around with transmit and receive chains.
100 megahertz 10-bit ADC.
I don't know. Like, why not? Why not? Okay.
Check out the design by Carsten Wolf, because he's published a paper on that's an A to D generator. So it's like and you can set that to like an arbitrary bit width, and he's published a paper on it if you want the performance figures.
There was a presenter at Latch Up this year at MIT who was starting a Wi-Fi receiver. He has like an LNA and some other pieces. Yeah.
Wi-Fi is good because you don't have the sharp mask.
Sure.
The mask is the big problem.
Yeah, indeed. Matt, I wanted to just ask another. Oh, sorry.
And we're still missing things like inductance modeling and extraction, which is also crucial for radio. But you know, if you just draw it out.
Give it a go.
Yeah, come on.
YOLO. So one question I wanted to ask, what is the biggest pain point at the moment for you with the analog design flow still today?
I mean, when I did my most recent design for the 1.8 to 3.3 volt step up, I was having to use bigger multi-finger transistors, and it probably took me 2 hours to wire them up without DRCs.
Yeah, sounds like a job a Python script might be able to do, right?
Yeah.
Well, layout automation, that's what I'm talking about.
Layout automation is
there are some projects like BAG.
a thing.
Hey. So what you were asking about are more like source revision control friendly
No, I think
input
it's
formats.
two different things. Yeah.
Okay. But because I do know that there are some projects for doing automatic generation of certain parts, and I guess with that you have a description language that is probably easier to do revision control of.
Yeah, exactly. Yeah, that's true.
So you have like Berkeley analog generator is one of these. PDK master is one of the other ones. There are more Coriolis.
All right. Yeah. Should we leave it there for now? Go drink some beer. Excellent. Thank you, Matt.
Thanks, everyone.